Welcome to this explainer. Okay, today we are diving into something absolutely massive. We're looking at how generative AI has totally transformed from being this rigid, strictly predictable tool into a fluid, probabilistic intelligence layer. Honestly, this shift is so profound that it literally requires us to build a whole new mental model if we want to understand, build, or even just work alongside modern software. So let's unpack this paradigm shift because it's a big one. For decades, literally decades, software engineering was entirely deterministic. It was rigid. You gave a system input X and you knew for a fact you'd get output Y. If something broke, debugging just meant hunting down that one exact line of faulty logic. But today's generative foundation models, they're totally different. They are probabilistic. Because they are constantly sampling from these incredibly vast learned probability distributions, giving them the exact same input might actually give you a slightly different output the next time around. In this new world, correctness isn't absolute anymore. It's statistical. Let's kick things off by looking at this shift, moving from pure automation to actual generation. Think about the incredible trajectory we've been on. Back in the 1950s, early AI was strictly symbolic. It was all rule-based, highly manual, and honestly, it completely panicked when faced with any ambiguity. Then we moved into statistical AI, which started learning patterns from data, and eventually hit the deep learning boom of the 2000s, which was great for things like image recognition. But now, we're in the post-2017 generative era, driven by transformer-based models. This is the ultimate shift. We've gone from automation to learning, and now to generation. Modern models don't just go fetch pre-written information for us anymore. They actively construct it on the fly. Okay, moving on. Let's actually peek under the hood and demystify the engine room of these large language models. First things first, and this is absolutely crucial to wrap your head around, these models don't comprehend language the way you and I do. There isn't a tiny little brain in there reading your words. Instead, they operate entirely through a probabilistic process that is firmly grounded in mathematical prediction. The bedrock of all this math is something called tokenization. Since machines obviously can't interpret raw language, they have to convert our words into sub-word units, which we call tokens. And it gets cooler, these tokens are then mapped to high-dimensional numerical embeddings. You can think of these embeddings like exact mathematical coordinates for words. This allows the model to perform insanely fast matrix algebra on modern hardware. So quite literally, our words become math. Once everything is translated into numbers, we jump into the generative prediction loop. The model takes your input sequence of tokens and calculates the statistical likelihood for what the very next token should be, relying on its massive training data. It picks one token, tacks it onto your sequence, and then bam, loops that entire process over and over again at blistering speed. We call this an autoregressive process. But here is where it gets really interesting. How does the model actually choose that next token? Well, if it always 100% of the time picked the most mathematically obvious next word, the text would be incredibly boring, just totally repetitive and robotic. To fix this, engineers introduce controlled randomness. By tweaking this dial of randomness, you can strike a balance. You can trade off between wild, highly creative, diverse outputs and strict, reliable consistency, all depending on whatever specific application you're trying to build. Right, so how do we actually talk to these things? Let's look at the art of prompting, where interaction becomes a form of communication. When you sit down and type a prompt, you are effectively doing behavioral programming. You're guiding the AI's reasoning pathway. You can use direct instruction, which is basically slapping down explicit constraints and formats, absolutely perfect for repeatable enterprise tasks. Or you might use conversational interaction, where you progressively refine what you want through a back-and-forth dialogue to explore really complex ideas dynamically. And then there's text expansion, which is amazing for blasting right past writer's block by having the model take a tiny initial thought and just run with it. The prompt is your operational bridge to the AI. Let's zoom out of it and look at the macro landscape, the foundation model ecosystem, and the whole open versus closed debate. We are talking about mind-blowing scale here. Thanks to empirical scaling laws, we know that as we crank up the compute power, the training data, and the parameter counts, the performance of these models just keeps surging. Frontier models today, like Meta's Llama 3, pack hundreds of billions of parameters. And the wildest part? Crossing these massive thresholds actually unlocks emergent capabilities. The models start doing things, like chain-of-thought reasoning, that engineers literally never explicitly program them to do. So if you're building in today's ecosystem, you have a massive strategic choice to make about how you deploy this intelligence. On one hand, you have proprietary API models, think like GPT-4o or Claude 3.5. This is essentially intelligence as a service. It's incredibly convenient, sure, but you're dealing with major vendor lock-in and completely opaque updates. On the other hand, you've got open-weight models like Llama 3. These let you self-host on your own hardware. That means you get deep parameter fine-tuning and total data sovereignty, but, and it's a big but, you take on the heavy burden of managing really complex GPU infrastructure yourself. Okay, on to our next point, which is a bit of an engineering reality check. Systems over single models. Let's be real for a second. Because these models are just playing the statistical odds, they inherently suffer from some pretty major structural limitations. The absolute biggest one? Hallucinations. The model is optimizing for what sounds plausible, not what is factually true, so it will confidently just invent facts. They also suffer from strict context window memory limits, meaning they forget things. They inherit massive data skews from their training data, and man, they are incredibly expensive to run computationally. And spoiler alert, you cannot fix these constraints just by being clever with your prompts. And that right there is exactly why generative AI isn't just about dropping a model into an app. It's full-blown systems engineering. Reliability only happens when you surround that core probabilistic model with a really strict coordinated architecture. You need a retrieval-augmented generation, or RAG, layer to ground the AI's responses in actual, verified data so it stops hallucinating. You need heavy guardrails for safety, memory systems to hold on to context, and rigid statistical evaluation frameworks to track quality. The LLM? It's just one tiny piece of a much larger puzzle. So, what does all this actually mean for us? Let's talk about the socio-technical impact and how this is reshaping the real world. The impact we are seeing across industries is just staggering. Take education. We're now able to scale highly personalized tutoring that actively adapts to a student's exact learning pace. In software development, AI is stepping in as this incredibly powerful co-pilot, helping developers with code generation and automating debugging. And in business and research, these models are synthesizing massive volumes of data to offer decision support like we've never seen before. These tools are rapidly becoming a universal, assistive intelligence layer that accelerates human capability everywhere. But, and this is crucial, we have to remember where these models learn from. They scrape vast oceans of human data off the internet. That means they automatically inherit our structural data skews and our informational blind spots. They are not purely technical artifacts, right? They are deeply socio-technical systems. Deploying them responsibly demands serious, disciplined governance, strict operational alignment, and really robust validation of the information they spit out. Economically speaking, the very nature of work is fundamentally shifting before our eyes. Because AI can now instantly generate baseline code, a first draft of a document, or initial analysis, the premium is no longer on pure content creation. Going forward, the massive premium in the workforce is going to be placed on human supervision, deep domain integration, and the strict validation of AI outputs. Which brings us to a final thought I want to leave you with. In this rapidly approaching new era, you're stepping out of the role of just being a creator. You're becoming the human supervisor of a highly plausible yet entirely probabilistic intelligence. So ask yourself, what steps are you going to take to guarantee the truth, safety, and integrity of the systems that you build and use every day? Thank you so much for joining me for this explainer. Catch you next time.